So it is a challenge to give a talk after Moti Jung. We both work in cryptography, and my approach when I started was essentially algorithms, crypto algorithms, but I've since moved to broader areas. One of the reasons why in the States people work in certain areas in security is because they get funding in certain areas. If you get a grant which pays for you to do some research, you work on that particular area. And currently there's a lot of funding in the States for systems which are complicated systems, structures, so I'll talk about those. So essentially, I will first talk about critical infrastructure ecologies. I use this term. Then I use the term resilience rather than security, and I'll explain why. And I will have three applications which I'm currently working on, and which somehow show how one can achieve resiliency or not achieve resiliency, whichever the case. So let me start by pointing out that the critical infrastructures are very complicated systems, and they are like ecologies. There is a sort of a cyber system, a control system which controls them, but they may involve social systems, physical systems, engineering structures, financial systems, the ecology, nature. And what the requirement basically is to have a kind of stability. The system must operate, and if you want it to be secure, it may be too much. Secure meaning that it should behave exactly as the specifications are. So in reality, in real life, sometimes you're willing to allow for faults to occur, provided you can manage the faults. So trying to manage the faults is very difficult, of course, because what happens is that there is an interconnectivity. All the systems are linked to each other, and a fault in one may have repercussions in the others. Indeed, if it's a malicious fault, if it's an attack, it can combine, it can use the fact of these interdependencies and exploit them. And that is exactly what happens in this. So essentially, the operating system can be controlled by the adversary, in which case it is almost impossible to sort of guarantee that the system will behave as intended originally. And therefore, I've also put here in this little box, I've just picked this up, this is from IBM. This is a sort of, I think there is a copyright for this. So this is IBM.com Outthink. So if everything is connected, it's very nice, of course, but of course then you also get everything is vulnerable. So it gives much more power to the user, but it also gives much more power to the adversary. And they also have somehow industries recognizing that things have changed. We are now in the cognitive era, and therefore you have to be able, if you want to survive, you have to outthink or outsmart the adversary. You have to be clever, you have to anticipate what the enemy will do with the adversary and take actions. So I think I'm going the wrong way around. Critical infrastructures there, I've put down 10 there. Principal ones are communication, finance, power, transport. I think Obama specified 16 areas. There are other areas. They all have this common feature that they exploit, they use their different technologies and they combine different areas. So they are ecologies in some sense. And the problem is that the services they provide are so critical for our society that if anything goes wrong, the effects may be devastating, and therefore it is important to find some kind of way of preventing the impact of these attacks to be serious. So this is where resiliency comes in. So resiliency is a new word which tries to capture what security used to be in the old days. It is a flavor of security, and so depending on what the application is, it has different facets, different expressions. So engineering systems usually want a kind of equilibrium steady state, so you're allowed to deviate from the equilibrium, but you must quickly recover and get back to the equilibrium state. That's what resilience is defined for engineering purposes. For ecological systems, there are natural perturbations. You may have earthquakes, you may have things going wrong in nature, and then what you would want is to recover from those perturbations. In socio-ecological systems, it's a balance of self-organizing systems. So if something goes, some system sort of is attacked by another system, then you want some kind of balancing to recover the system. And the financial system definition is interesting because it looks at the another aspect which is extremely important. It is the ability to recover, to adapt to consequences of failure. So failure will occur, you just have to accept it, and the question is sort of you have to redesign your structure, your system, so that it can recover from it. So they are all different facets of the same requirement, and a proper definition of resiliency would capture all of them. The threat model is quite sort of extensive. Traditionally, in cryptography, you just look at the focus was just on bad actor or malware behavior. Indeed, it was malware behavior. Bad actor usually refers also to state actors, which is a critical threat in the case of cyber-physical systems. But one has to take in nature also. This is a tsunami. I think this slide was shown earlier. Faulty design. I'm now thinking of critical infrastructures. So these are complex interdependent structures. And adversarial actions. So the NIST, which is the National Institute of Standards, the USA, has somehow divided, captured the resiliency of, they still use the term security, of a cyber-physical system as consisting of, say, of 5 steps. And I've highlighted some of them which are of interest to us. So the idea is essentially the first one to identify any sort of faults in the system, any misbehavior. And misbehavior would be unexpected behavior, behavior different from what you expect the system to do. And the strategy, the approach typically used involves assessing the risk if things go wrong and trying to manage it if the consequences are serious. And this is before a threat happens, attack happens. This is just potential threats. Then the idea is to devise technologies or mechanisms or tools which will address these potential threats and prevent them happening. So normally in security you would stop there because you would assume that somehow that it is possible to find all possible threats and all possible to protect yourself holistically against all possible threats, and then that there wouldn't be any other consequence because the attacks would never take place. But in reality, what happens is you always have an event. An attack will take place, so there will be an event. So the term usually is used for an event, a bad event, and then the question is you have to respond to the event and then recover, build again, and then the whole cycle is repeated. So this is captured with this event cycle for critical infrastructures. It more or less splits the steps into pre-event steps and post-event steps. So then it automatically, it assumes by default that there will always be events. Things will always go wrong. The systems are so complicated, so complex that it is impossible to deal with every possible threat. Indeed, the code for some of these systems is so large, I'm talking about 50 or 60,000 lines, that even the faults in the code, the vulnerabilities, the exploits are measured in thousands. And you can never, you fix one, you patch one, and then there are more coming. So this is ongoing. It has to be by definition ongoing. And so the idea is that there has to be some kind of mitigating the event, and then recovering from it, and the whole cycle is repeated. So this is a continuous approach. So resiliency is not something static, it is dynamic. Security now, we have to look at it in a different way. It has to continuously address issues and adapt dynamically to the new state of the system. Okay, so there are different ways of looking at it. I'm still talking about generalities of how to sort of understand the procedures which are needed to create or to generate such a sort of architecture which would dynamically address these threats. And one of them is perhaps to understand exactly what the adversary is, what the intent of the adversary and the scope is. So that means that rather than looking at everything the adversary can do, you just look at the things the adversary is likely to do now. And that restricts your scope significantly. What is in the interest of the adversary? Why would the adversary do certain things? And then find the features that such an adversary would want to abuse. And then find out what the consequences to the system as a whole, on the social, economic, or political institutions are, because we are now talking about this critical infrastructure from these attacks. So you try to single out the attacks which a potential adversary would get involved in, and then find how you can sort of address them. And ultimately, maybe you cannot address all of them. It may be too expensive. Indeed, the next slide will involve a game theoretical approach in which you take into account the cost, and that is an important factor. And so the idea is the cost will determine to what extent you will try to redefine your sort of equilibrium surface. And the next thing would be, so there are certain features I've addressed, system features that can be abused. This is a generic term. You actually have to look for vulnerabilities. And there are various ways in which you can look at vulnerabilities. You can study the requirements of the policies, because systems are defined to match certain policies, and the policies themselves may be the cause for vulnerabilities. And then there are various other ways of doing it, which people working with code know very well, which have to do with assessing vulnerability and gray box penetration tests. There are various tests which can be done, and they can single out certain specific types of vulnerabilities. Again, this is never holistic. It just picks out the ones you can easily find. And finally is to develop technologies which somehow can be used as a kind of basis for your analysis. So it may be that certain threats are just left as sort of unprotected. It may not be worth your while to aiming for certain kinds of protections. For example, in certain types of cyber-physical systems, privacy leaks are not so important. What is more important is integrity. So if you have a nuclear power station, you want to know exactly what the state of the system is. If the adversary can monitor the state of your system, you don't care too much about that. Because the consequences of an integrity violation, something going wrong with the system, are far worse than the consequences of leak. Then financial and models. So there are different models which somehow take into account the utility of the protection, the cost, utility cost, and try to work out a kind of an optimal solution. And then use cryptographic tools and mechanisms, which another way of dealing with it. So the game theories is one nice model for doing it, but it's quite useful for using it. It looks at the problem as being a sort of more from a military point of view. So there's a strategic decision making. You know what the risks are, you know what the threats are, and you just have to decide what you will protect and how you will protect. And what you do your decision is made based on essentially utilities. You cost the sort of the various consequences of the actions, adversarial actions, and then you try to optimize and find a balance, a sort of an equilibrium state in which you will aim for. And ultimately, this is the one which will give you this balanced system state. And the cryptographic tools are typically the ones which have been around for the last 40 years, 50 years. The standard ones and the ones which Morty Jung talked about this morning involve confidentiality and integrity. Availability sometimes is always put on the borderline, as it's not clearly defined what availability is in specific terms. For example, availability could be sort of best effort availability. That's the one we get for the internet. So if you want bandwidth, if the system has some bandwidth, it gives you, but it doesn't give it to you in milliseconds or microseconds. It gives you a good average. Quality of service is something like that. For many applications, this is not good enough. So what really one needs is something which I call need to get now access, instant access. So if you have a nuclear power station and something goes wrong, you cannot wait. You don't have you don't have allowances for an average good time. Say average good time may be something like 2 or 3 seconds. 2 or 3 seconds may be too much. You may want 2 milliseconds. The decision has to be made in 2 milliseconds. So then you have to use another kind of approach, which is in which availability completely is different. It's not traditional availability. It's an availability which is in real time. I mean, you cannot require instant availability because it doesn't make sense. So it has to be in time, but your time must be much shorter. And within that time window, you must get it. So there are power plants, electricity power plants, in which in 4 milliseconds a fuse will melt, and the whole system will have cascading errors, and the whole system will go down. So within those 4 milliseconds, you have to address the issue. So you need something like 2 milliseconds or less. Trusted computing has been around. Morty isn't here, but this goes back to 1990. You are around, sorry. And it's been a sort of the goal. In cryptography, for systems, you always looked at this ideal situation where you could actually guarantee that the applications will be trusted, will run as they're supposed to run. So this is for integrity, not privacy. And the question is, so you want to know if your program will execute statically or dynamically, because it may be statically correct, but when you run it, things may go wrong. And of course, sorry, I've jumped too much. And you may also want to know that within a given time window, everything is available, not outside that window. And the architectures, there are some, you can get sort of laptops which have chips, which will offer this kind of protection. Many people complain about it. It depends how you implement it. The advantages of it is that from the point of view of the industry, from the users, it offers antivirus protection, and you can turn it off if you don't like it. For industries, you can license it. It offers some kind of security, and industry also likes it because of it's standardized. So now I'll talk about the 3 applications I wanted to talk about. And the first one has to do with emergency. So emergencies. And again, this is part of the cycle of resiliency. So if things go wrong, you have to address the emergency, respond with it, and recover and come back, mitigate. So this is the same cycle. And this is work with Jorge Munilla, and it has to do with supply chain management. So if you I will take a version of supply chain management which has to do with emergencies. So in supply chain management, you have an owner of goods, of tagged goods, and then you have and the tagged goods are handed over to a carrier who is supposed to carry them and take them to the destination. The owner sometimes can relinquish the rights and give the rights to the carrier, and then, of course, there's no problem. But in many cases, the rights are not relinquished, so the carrier is not treated as a trusted entity. The carrier does not share any secret keys or is regarded as an untrusted entity. So whereas the owner is the trusted entity, the tags are regarded as trusted entities, and so the owner must be able to somehow to know that the goods, to have ways of checking the integrity of the goods while they are transported to the destination. In this model, we have Alice is the owner, Bob is the carrier, and the link between Alice and Bob is through the internet, and it's a sort of expensive for Bob this link is sort of rather one way, so Alice is not online all the time. So what Bob the carrier has to do, he has a device, a mobile device, and he has a sort of collection, a palette consisting of tagged objects, and he wants to check that all the tagged objects are there. So the requirement here is that if all the tagged objects are there, this device, which shares no keys, is untrusted, it shares no keys with these tagged objects, should be able to generate a proof, a grouping proof, which the owner can check and verify the integrity of the collection of tagged objects of the palette. And if something is missing here, the carrier should be able to identify the missing objects and inform or send the owner that the integrity is lost, there isn't integrity, the proof cannot be generated because some of the tags are missing, and the owner will have to deal with this issue. The advantage of this kind of protocol is that essentially when it starts, the carrier gets a confirmed palette with all the objects. So somewhere along the line, some of the objects have lost, and the carrier can report back to the owner when this happened. That's the only responsibility of the carrier. So this is a challenging protocol. And the idea is essentially, now where does it come to emergencies? you have these tags, which sort of in the States, this FEMA that usually does, this is the body who deals with emergencies. You have pallets which are supposed to have everything in, and when an emergency happens, like with Katrina, you send these pallets and they sent almost immediately to the destination. You open them up and you find that some of the things are missing, and therefore you can't do things. So the idea is you want to be able to have a device, a mobile device, which tells you immediately that does the checklist, and before you even send it, you check it and you know that something is missing. And the protocol, I should have put down the protocol. I noticed that it would have been interesting. It assumes, so with RFID tags, you have to base your protocol on devices which have practically no computing power or very little computing power. So in this case, the standard for RFIDs is that they should be able to sort of compute a pseudo-random number, and they work out the hash value, nothing else. And the protocol, of course, needs somehow, if you don't share any keys with another party, it would be impossible to communicate securely with the other party, so you get a one-time authenticator from the verifier, so that is used by the reader, which is untrusted, so it just gets a one-time authenticator and a counter value, and that somehow, from the point of view of the tags, identifies the reader as an authorized reader to check the session. The other application, which now gets much more complex, this is what is called a substation of an electrical grid. There are two parts. Sorry, I moved too fast. And there's this part, which is in the switch. This is outside. This is where all the equipment, heavy equipment, and this is where all the intelligent devices are. So the monitors are inside in this control house in the yard, and they monitor the system. And if these do, so there is the next slide shows how much time do I have? You are great. Okay. So this is the bottom part here. There are merged units. These are the sort of transformers and the sort of and this is how they got. So at this stage, this is in the yard. So behind the yard in the room, there's all the relays and the intelligent electronic devices which monitor what happens, and they have a very short span. They have within 4 milliseconds, they must decide whether there is some anomaly or not anomaly in the readings they make. And this actually captures General Electric. So there are very specific standards for this type of implementation. The standard is the IEC 61850, which is implemented by General Electric, but also by there's also other manufacturers in Germany. Siemens does something like this, and the Chinese, of course. So there is the system allows for a human-machine interface, so there's some human here who can check things, and the vulnerable point here is the internet. So there are advantages, and so there's it is possible as essentially with your cell phone to control the system for controllers outside. That would be an advantage, say, for example, for the Japanese nuclear power disaster, because what would happen is there were people in Tokyo who knew that this earthquake had happened, and they knew that if an earthquake happens in Japan, this is always, everybody knows that, you get a tsunami effect, and then what you should do is you should start the sort of shutdown procedure immediately, because it takes half an hour to shut down a nuclear power, so just a little bit. So if that had happened, the disaster would have been far less serious. And on the other hand, like I said before, if everything is connected, everything is vulnerable. So this same channel can be used by the adversary. So then the question is, maybe some of these devices have malware. Maybe they are sort of tampered. So what has to be done is to see to what extent. Of course, GE claimed that this is impossible. They use a special type of fiber which prevents this, and their equipment cannot be sort of manipulated. But so the idea is, so we got a large award to check this. The idea is to actually emulate, to get, so we got all this equipment, which isn't cheap, and then there is what is called a real-time digital simulator. So there is a simulator which simulates the behavior of an electrical power grid. And this is a very complicated structure, and very expensive. So the idea then is to actually take the real equipment and sort of use what is called hardware in the loop. You put it in the system and you try to manipulate it, see what, use stress testing. For example, one of the attacks which was thought, which is quite risky, but effective, is to attack the meter. So the meter will show normal readings while the system is not normal. And therefore, you would it would be impossible to detect anomalies because this would always show normal. The readings would always be what you would expect to see at that point in time. And there is malicious-ware that can do that. That's one attack. The other one is sort of to create irregularities here. But this is another project. The third one, and my last one, has to do with implantable medical devices. The problem is, I try to sort of look at security from a resiliency point of view, where you know that things will go wrong, so then you have some kind of game theory approach where you try to minimize the impact of certain types of attack. So by addressing those attacks, and there were other ones which do not have a serious impact, you just forget about them. And so you negotiate yourself. You do a clever risk management strategy. And the question is, will this work for implantable medical devices? So these are sort of, they can be partially or wholly. So the pacemakers are the best example. So you can have used pacemakers, or all sorts of this. As medicine progresses, these become much more. So the developments in this particular area is enormous. Every year, pacemakers of 2015 are about 10 times better than those of 2012. So in every 2 or 3 years, they do much more. So today's pacemakers are holistic. They are devices which actually link up completely in a full system, as I will show in the next slide. This is a sort of, so this is an example. So this is a Bob, he's a patient, he's a pacemaker, and his pacemaker, and this is a doctor who can monitor through a complete system via the internet. So this is what a pacemaker today can do. So a medical officer or a healthcare professional can almost continuously monitor a patient in that way. The question is, there are lots of little red little devils here, and these are the places where so this is an ecology, you can think of it. It's a complete system. It is highly networked. Everything is networked. It involves a human. It involves physical objects, cyber, everything you can think of. And of course, everything is vulnerable to attack. And the question is, where do you focus your sort of analysis on, or your risk management? Do you think of, I mean, if it's resiliency, if a few patients die, do you say that that's not that important? I mean, at least 90% of the patients survived. So it is very difficult to deal with such cases. And the only way we can think of dealing is protecting bits by bit. So you protect, for example, this part here, and have some kind of way of preventing anything going wrong, and then you risk the thing that the doctor may not get the right information. And so at least the risk is that the latest version of the technology fails, but the earlier versions are there, so that somehow something else will go, or some others. This is very difficult. I mean, I don't really know how to address this case, but this is a case where you cannot mitigate utilities. You cannot actually put utilities on human life, or I mean, if you do, the moment you do, then something goes wrong. So that kind of approach doesn't work. Okay, so I think that's my last slide. Thank you very much.